By now you may have noticed that when we find the area underneath a curve, like this one, let's say between this point and this point, what we're actually finding, is the area between the curve and the x-axis. And so if this were the curve x squared, then by integrating x squared, let's say that this is point A, this is point B, by integrating x squared with respect to x from point A to point B, what we're doing is that we're finding the area, not merely under the curve, but specifically the area between the curve and the x-axis between the points A and B. Finding the area between a curve and the x-axis becomes a bit tricky when this happens. So we have the curve and it goes under and above. So we want to find the area between the curve and the x-axis between this point and this point. So we're going to be adding the area here to the area here. And that will tell us the entire area between the curve and the x-axis between these 2 points A and B. So here's a trick. Whatever area we get here, let's say we get x units squared. This x will be a negative number because the area is below the x-axis, while this area being above the x-axis would be a positive number. So if we call it p units, then p will be a positive number because the area above the x-axis will always be positive, while the area below the x-axis will be negative. So what's the issue? The issue is, if I were to say I'm going to find the area between A and let's say that this is Q. If I were to find the area between A and Q, I'm going to get a negative number. And I find the area between Q and B and get a positive number. Instead of, when I add them together, instead of getting the true sum of the area between A and B, I'm going to be getting the difference between the area here and the area here. And what that would mean for me is that I would not have found the true area between that curve right here and the x-axis between the points A and B. So what do? I take the integral of that very same function, f of x, and I integrate from A to Q. But I find the modulus of that and add it to the integral of that same function from Q to B. That will give me the area between this curve and the x-axis. If the area between the curve and the x-axis between A and Q is equal to the area between the curve and the x-axis between Q and B, then if we don't find the modulus here, what will happen is that we will end up having an area of 0, because this being, let's say that this was equal to negative A and this were equal to A. Adding them together, that would be suggesting to us that the area under the curve, or the area between the curve and the x-axis, would be 0 units squared, which we know for a fact is not true. And in the last example, we attempted to find the area under the curve for sine 6x, sine 2x, and we got that the area under the curve is 0. But that's not true. We got that the area between this curve and the x-axis between 0 and pi over 2 is 0. But we know that's not true. How do we know that? If we look on the curve of 4 sine 6x sine 2x, we notice that finding the area between 0 and pi over 2 requires that we find the area here between 0 and pi over 6, the area here between pi over 6 and pi over 3, and the area between pi over 3 and pi over 2. Now, what happens is that the area here, the sum of the area here and here, is equal to the area between pi over 6 and pi over 3. So what happens? What happened here is that, let's say that the area here is A units squared. Integration is going to give us a negative value when we find the area of this section between pi over 6 and pi over 3. And the sum of the area between 0 and pi over 6 and pi over 3 and pi over 2 will give us the same A units squared. And so their sum gives us 0 units squared. So what we're required to do then is to find the area of the section between pi over 6 and pi over 3, and then find the absolute value of that area, and then we can add it to the area of these sections between 0 and pi over 6 and pi over 3 and pi over 2. So let's go ahead and do that. So integrating 4 sine 6x sine 2x with respect to x from 0 to pi over 6, that's the first part, plus the integral from pi over 6 now to what? Pi over 3 of 4 sine 6x sine 2x. But what happens here? We have to find the absolute value of that. Oh, we're supposed to be integrating with respect to x. So yes, finding the absolute value of that and adding that now to the integral of the very same thing, 4 sine 6x sine 2x with respect to x from pi over 3 now to pi over 2. And our job is done, because having integrated, we know that our first part of the sum will be root 27 over 8 units squared, plus what? Root 27 over 4 units squared, plus root 27 over 8 units squared. And what does that sum to give us? We get 27, or rather root 27 over 2 units squared. And that is the true area under the curve that we are assessing, which is 4 sine 6x sine 2x between 0 and pi over 2. Now remember that on a Cartesian plane, we have not only the x-axis but also a y-axis. We can be required to find the area not between the curve and the x-axis, but between the curve and the y-axis. So if that is the case, and we have to find the area here of this curve y equal x cubed, all we need to do is to integrate not with respect to x, but rather with respect to y. So if we're integrating with respect to y, then our function has to be in terms of y. So instead of having y is equal to x cubed, we're going to make x the subject, and we're going to say x is equal to y to the 1/3. Y to the 1/3 power. And what do? We want to find the area between this curve and the y-axis from 0 to 5, from y equals 0 to y equal 5. So how do we go about doing that? We integrate y to the 1/3 with respect to y from 0 to 5. And what do we get? We get y to the 4/3 divided by 4/3, which would give us 3/4. And we're doing that from 0 to 5. If we substitute 0 in there, we're going to get 0. So all that would leave us with is substituting 5 in it, giving us 6.4124 units squared. So now we know how to find the area between a curve and the x-axis and between a curve and the y-axis.